On December 29, 2024, a telescope in Hawaii recorded something that shouldn't exist. Not a star, not a planet, not debris from our solar system's ancient past. An object, moving fast, coming from somewhere else. The Atlas Survey Asteroid Terrestrial Impact Last Alert System flags thousands of rocks every year. Most are ordinary, predictable, chunks of ice and stone that follow the rules written 4.5 billion years ago when our sun ignited and the planets began their endless dance. This one didn't follow the rules. The first anomaly appeared in the data within hours. Velocity, 137,000 miles per hour relative to the sun. That alone means nothing. Comets move fast. But the trajectory, the path it carved through space, told a different story. It came from outside, from the space between stars. Interstellar objects are rare. Before 2017, we had never confirmed one. Then came Oumuamua, the cigar-shaped wanderer that passed through our system and sparked years of debate. In 2019, Borisov arrived a comet so ordinary it almost disappointed us. And now in late 2024, this the third confirmed interstellar visitor. They named it C-2024 Atlas, or simply 3I Atlas. The 3I marks it as the third interstellar object ever catalogued by humanity. The designation feels clinical, bureaucratic, a label for something that defies easy categorization. But labels don't capture what happened next. Within weeks, observatories across Earth turned their instruments toward Atlas. Spectroscopy revealed its chemical signature, the light it reflected, the elements it carried, and that's when the data stopped making sense. Nickel. Atlas was emitting nickel vapor, not trace amounts, not faint signals buried in noise. Clear, unmistakable emission lines in the visible spectrum. A team led by Avi Loeb confirmed it with over 4,000 observations from the TAN-1 telescope. Nickel emission from a comet isn't impossible. Rare, yes, but not forbidden, except for one problem. There was no iron. Nickel and iron are siblings in the cosmic story. They form together in the hearts of dying stars, fuse in supernova, and drift through space as inseparable companions. Every meteorite that strikes Earth, every asteroid we've sampled, every comet we've studied, if nickel is present, iron is present. Always. It's not a preference, it's chemistry, it's physics, it's the way the universe works. Atlas broke that rule. Imagine finding a shadow without an object to cast it. Imagine hearing an echo in a room with no walls. That's what the spectroscopic data suggested, a chemical impossibility written in light. The second anomaly emerged when scientists calculated the outgassing rate. Comets lose mass as they approach the sun. Ice sublimates into vapor, dragging dust and particles with it. This process creates the tail, the iconic glow that transforms a frozen rock into something beautiful. Atlas was losing mass too, about 150 kilograms per second, expelled at 440 meters per second. The numbers fit. What you'd expect from a comet. But comets that outgas also accelerate. The escaping vapor acts like a tiny rocket engine, pushing the nucleus in the opposite direction. It's subtle, but measurable, a deviation from the gravitational pull of the sun. Atlas showed no such acceleration. It expelled material with the force of a jet engine. And it didn't move. Think of it like this. You're standing on ice, and you throw a heavy ball forward. Newton's third law says you slide backward. There's no escaping it. Action and reaction. Momentum must balance. Atlas threw the ball and stayed perfectly still. The third anomaly appeared when astronomers plotted its orbit. Interstellar objects can enter our solar system from any angle. Space is three-dimensional, vast and chaotic. The odds of an object arriving along the ecliptic plane, the flat disk where Earth and the other planets orbit, are incredibly low. About 0.2%, 1 in 500. Atlas arrived almost exactly on the ecliptic, not tilted, not skewed, aligned, as if it knew where the planets would be. Now, probabilities are tricky. Rare things happen. Lottery winners exist. Lightning strikes the same spot twice. A 0.2% chance is not zero. But when you find 3 anomalies in one object chemistry that violates known processes, physics that ignores momentum, and a trajectory that defies randomness, you stop thinking about luck. You start asking different questions. What if this object is not a comet at all? The data comes from real instruments. The Minor Planet Center in Cambridge, Massachusetts, tracks every confirmed observation. NASA's Mars Reconnaissance Orbiter, ESA's Trace Gas Orbiter, and Mars Express prepared to study Atlas during its closest approach to Mars, scheduled for October 29, 2025. 18 million miles. Close enough for detailed spectroscopy. Close enough to resolve features on its surface, if it has a surface. Close enough to answer the question that nobody wants to ask out loud. Is Atlas natural, or is it something else? 2 possibilities. 2 very different implications. If Atlas is a comet, then we've discovered a new kind of chemistry, a new class of interstellar object that formed under conditions we don't yet understand. Our models of stellar evolution, planetary formation, and the behavior of matter in deep space would need revising. Textbooks would be rewritten. That alone would be extraordinary. But if Atlas is not natural, if it's artificial, a probe sent by an intelligence we've never met, then the implications stretch far beyond chemistry and physics. It would mean we are not alone. It would mean someone else is out there, watching, listening, perhaps even waiting. And it would mean that on October 29, 2025, as Atlas passes Mars, we might receive an answer to the oldest question humanity has ever asked. The perihelion, the point of closest approach to the Sun, arrives 3 weeks later, November 17, 2025. That's when Atlas will be at its brightest, most active, most observable. That's when the data will either confirm the anomalies or explain them away. Mark that date, because either way, we're about to learn something profound about our place in the universe. The countdown has already begun. If Atlas is a comet, it's the heaviest one ever observed. Comets are usually light, fragile, chunks of ice and dust held together by weak gravity and frozen volatiles. When Halley's Comet last visited in 1986, scientists estimated its mass at roughly 220 billion kilograms, about the weight of a small mountain. Atlas, by contrast, has a minimum mass of 33 billion metric tons, 33 trillion kilograms. To put that in perspective, if you lined up 500 of the world's largest aircraft carriers and stacked them together, you'd approach the mass of Atlas. And that's the minimum estimate. The calculation comes from the outgassing data. When a comet loses 150 kilograms of material every second, you can work backwards estimate how long it's been active, how much mass it's already lost, and how much remains. The math is straightforward, the result is not. A comet that massive shouldn't behave the way Atlas behaves. It should fragment under its own gravity. It should show signs of internal structure layers, fractures, spin rates that correlate with density. It should accelerate from outgassing, because even a small force applied to a large mass over time produces measurable motion. Atlas does none of these things. It expels material without accelerating. It remains intact without visible fractures. It moves through space as if momentum doesn't apply. Unless it's not a comet. Let's consider the alternative. If Atlas is artificial, a manufactured object, then the mass makes more sense. A probe designed for interstellar travel would need to be massive, heavy shielding against radiation, redundant systems for navigation and communication, fuel if it uses propulsion, structure strong enough to survive millennia in the E-void. But even that explanation has problems. Why would an artificial probe outgas like a comet? Why emit nickel vapor? Why arrive on the ecliptic plane? Unless those aren't accidents, unless they're signals. Nickel emission could be intentional, a marker, a beacon, something designed to catch the attention of anyone with a spectroscope pointed in the right direction. The absence of iron makes it memorable, an anomaly that stands out against the background of natural objects. The ecliptic. Alignment could be navigation. If you wanted to visit a solar system's inhabited worlds, You'd aim for the plane where planets orbit. You'd maximize your chances of encounter. And the lack of acceleration? That could be control. A system that compensates for outgassing thrust, a way to maintain trajectory despite mass loss. These are speculations, not facts, not conclusions drawn from data, but they're speculations that fit the data better than the natural explanation. Here's what we know for certain. Atlas will pass within 18 million miles of Mars on October 29th. That's 40 times closer than Earth. Close enough for every Mars Orbiter, MRO, TGO, Mars Express, to turn their cameras and spectrometers toward it. Close enough to measure its size, its shape, its rotation, its surface composition. Close enough to see if it's emitting signals we haven't detected yet. NASA hasn't issued a statement calling Atlas artificial, neither has ESA. The Minor Planet Center lists it as a comet. The working assumption remains natural until proven otherwise. But working assumptions can change. In 2017, when Oumuamua passed through our system, scientists measured its acceleration and found something odd. It sped up as it moved away from the Sun too much to be explained by outgassing alone. Some proposed that it was a hydrogen iceberg, an exotic form of comet we'd never seen before. Others suggested it might be a light sail, a thin reflective sheet pushed by sunlight. Avi Loeb, the astronomer, who confirmed Atlas's nickel emission, was one of the scientists who considered the artificial hypothesis for Oumuamua. He didn't claim proof, he didn't demand belief. He simply asked, what if? That question matters, because if we dismiss the possibility of artificial objects before examining the evidence, we risk missing the most important discovery in human history. And if we assume every anomaly is artificial before exhausting natural explanations, we risk losing credibility, rigor, and the scientific method itself. The balance is delicate. Atlas gives us 3 weeks to find it. The mass data will sharpen as observatories continue tracking the object. Infrared telescopes will measure its thermal signature, how much heat it radiates, which correlates with size and composition. Radar observations might be possible if Atlas comes close enough, offering direct measurements of its surface. But the most critical observations will come from Mars. The orbiters there carry instruments designed to study the Martian atmosphere, surface, and potential biosignatures. They weren't built to analyze interstellar objects, but they're the best tools we have at that distance. If Atlas has a structured surface panels, antennas, geometric features, the cameras will resolve them. If it emits radiation in non-visible wavelengths, radio, microwave, infrared, the spectrometers will detect it. And if it changes trajectory as it approaches Mars, if it maneuvers in ways that gravity alone cannot explain, then the mass problem stops being a problem, because mass doesn't matter if you have thrust. 3 weeks until Mars, 4 weeks until perihelion, the data is coming, and the universe doesn't care whether we're ready for the answer. Nickel without iron is like finding water without oxygen. Not rare, impossible. Let's start with how nickel forms. Deep inside massive stars 8 times the mass of our Sun, or larger nuclear fusion, climbs the periodic table. Hydrogen fuses into helium. Helium into carbon. Carbon into oxygen, neon, magnesium, silicon. The process continues, each stage requiring higher temperatures and pressures until the star's core becomes iron. Iron is where fusion stops. Fusing iron consumes energy instead of releasing it. The core collapses. The outer layers rebound in a supernova, an explosion so violent it briefly outshines entire galaxies. In that explosion, heavier elements form. Nickel, cobalt, copper, zinc, gold, uranium. Nickel and iron are born together in the same stellar furnace. They drift through space together, condense into clouds together, and eventually coalesce into asteroids, planets, and comets together. Every sample of cosmic material we've ever studied confirms this. Meteorites contain iron-nickel alloys. Asteroids show spectroscopic signatures of both. Comets from the Oort cloud carry trace metals in their ice, and when nickel appears, iron appears alongside it. Atlas breaks that pattern. The SWAN telescope, operated by Avi Loeb's team, collected over 4,000 spectroscopic observations of Atlas between January and March 2025. The data showed clear emission lines at 341.5 nanometers and 352.5 nanometers wavelengths, characteristic of neutral nickel atoms. The team searched for iron emission. They looked at the expected wavelengths: 372 nanometers, 382 nanometers, multiple other lines where iron should glow if present. Nothing. Not faint traces. Not marginal detections. Absence. The simplest explanation would be that iron is present, but not emitting, perhaps locked in compounds or too cold, or somehow hidden in the spectroscopic noise. But nickel and iron behave almost identically under the same conditions. If nickel is hot enough to emit visible light, iron should be too. If nickel is in vapor form, iron should be too. If solar radiation excites nickel atoms, it should excite iron atoms just as easily. The chemistry doesn't allow for nickel alone. Unless Atlas isn't made of natural materials, consider an artificial object, a probe. If you were designing something to travel between stars, you'd choose materials based on function, not cosmic abundance. You'd want strength, durability, resistance to radiation. You might use alloys, combinations of metals engineered for specific properties. And if you wanted to mark your probe as artificial, you might choose an emission signature that violates natural expectations. Nickel without iron would do that. It's a hypothesis, not a conclusion. But it's a hypothesis. That fits the observation better than any natural process we currently understand. Now let's talk about what happens when spectroscopy fails to explain an object. In 1995, astronomers discovered 51 Pegasi b, the first exoplanet orbiting a sun-like star. Its properties made no sense. It was a gas giant similar to Jupiter, but it orbited its star every 4 days. Gas giants shouldn't exist that close to their stars. Our models said they form far out, where it's cold enough for ice to condense. The discovery didn't break physics. It broke assumptions. We learned that planets migrate, that solar systems evolve in ways we hadn't predicted, that our own solar system might not represent the norm. Atlas might be doing the same thing, forcing us to revise our assumptions about comets, about interstellar objects, about how matter behaves in the space between stars. Or it might be teaching us something else entirely. The European Space Agency's Trace Gas Orbiter, currently in Mars orbit, carries an instrument called NOMAD Nadir and occultation for Mars discovery. It's designed to detect methane and other gases in the Martian atmosphere, but it can also perform spectroscopy on objects passing nearby. When Atlas makes its closest approach on October 29th, NOMAD will have a chance to capture high-resolution spectra. Better data, more wavelengths, longer exposure times. If iron is present but weak, NOMAD might find it. If other metals are emitting cobalt, chromium, manganese, NOMAD will detect them. And if the emission signature remains impossible, if the chemistry continues to violate every known process, then we'll have to accept one of two conclusions. Either we've discovered a new type of stellar nucleosynthesis, a process that produces nickel without iron, under conditions we've never observed or theorized. Or we've discovered something that wasn't made by a star. Both options reshape our understanding of the universe. One expands chemistry, the other expands history. The question is, which answer are we hoping for? Because hope is part of this now. Scientists don't often talk about hope. We talk about data, models, probabilities. We avoid emotional language because it clouds judgment. But when you spend your career searching for life beyond Earth, when you build telescopes and probes and algorithms designed to find signals in the noise, you can't avoid hope entirely. You hope the universe is less empty than it seems. You hope intelligence is more common than our solitude suggests. You hope that one day the data will show something extraordinary, and you fear that when it does you won't recognize it, because intelligence might not look like us. It might not think like us. It might not build things the way we build things, or send signals the way we'd send signals. It might emit nickel vapor for reasons we can't fathom. It might travel along the ecliptic plane for purposes we can't decode. It might expel material without accelerating because momentum means something different to whatever designed it. Or it might just be a comet, a weird, improbable, chemistry-breaking comet. We'll know soon enough. 3 weeks until Mars, 4 weeks until perihelion. The spectroscopy data is coming, and with it, an answer that won't satisfy everyone but will certainly surprise. Space is three-dimensional, infinite, chaotic. Objects entering our solar system from interstellar space can arrive from any direction above the ecliptic plane, below it, tilted at wild angles that reflect the randomness of the galaxy. Oumuamua came in at 122 degrees relative to the ecliptic. Borisov entered at 44 degrees. Both were tilted, skewed, exactly what you'd expect from objects that formed light years away with no connection to our solar system's geometry. Atlas arrived at 2 degrees, almost perfectly aligned with the plane where Earth, Mars, Venus, Jupiter, and the other planets orbit, almost flat, almost intentional. The probability of that happening by chance, about 0.2%, 1 in 500. Now let's be careful with probabilities. They measure likelihood, not impossibility. Rare events occur all the time. If you flip a coin 10 times, the odds of getting a specific sequence say heads, tails, heads, heads, tails, tails, heads, tails, heads. Tails are about 1 in 1,000. Improbable. But if you flip the coin, you'll get some sequence, and whatever sequence you get will have been equally improbable. Rarity doesn't equal significance, except when it does. Atlas's trajectory isn't just rare, it's useful. If you were sending a probe to explore a solar system, you'd aim for the ecliptic plane. That's where the planets are. That's where water might exist. That's where life, if it evolved, would most likely be. You wouldn't approach from above or below, wasting time and fuel to adjust your trajectory. You'd aim for the plane from the start. Atlas did exactly that. The Minor Planet Center published its orbital elements in January 2025. Eccentricity, 1003 slightly hyperbolic, confirming interstellar origin. Inclination, 2.04 degrees almost flat. Perihelion distance, 0.65 astronomical units, which places it closer to the Sun than Venus. Everything about the orbit suggests a deliberate path. But orbits don't reveal intent, they reveal physics, gravity, velocity, trajectory. Those are determined by where an object came from and how fast it was moving when it entered our system. If Atlas formed in another star system and was gravitationally ejected, flung out by a close encounter with a planet or binary star, then its trajectory is random. The fact that it happens to align with our ecliptic is coincidence. Unlikely, yes, but not forbidden. Unless Atlas didn't form in another star system, unless it was launched. Launching an object between stars requires enormous energy. You need to accelerate it to a significant fraction of light speed, tens of thousands of kilometers per second, to cross the distances in reasonable time. Even at 137,000 miles per hour, Atlas would take tens of thousands of years to travel from the nearest star. That's slow by cosmic standards, but it's fast enough. And if you're launching something, you aim it. You don't eject it randomly and hope it finds a target. You calculate trajectories, you account for the motion of your target star, the orbits of its planets, the time it will take to arrive. You aim for the ecliptic. This is speculation, not proof, but it's speculation grounded in the logic of interstellar travel. If Atlas were natural, a rogue comet ejected by gravitational chaos, it would statistically be more likely to arrive at a high inclination. The galaxy doesn't care about our ecliptic plane. The odds favor randomness. But Atlas isn't random. It's aligned. Now consider the timing. Atlas was discovered in December 2024. Its closest approach to Mars happens in October 2025. Its perihelion, the moment when it's nearest the Sun, most active, most observable, occurs in November 2025. 10 months from discovery to peak observation. Just enough time to organize a global campaign, to coordinate telescopes, to prepare Mars orbiters, to analyze data as it arrives. If you wanted to be seen, that's how you'd do it. You'd arrive with enough advance notice that scientists could prepare. You'd pass close to planets with orbital infrastructure, Mars in this case. You'd time your brightest moment for when Earth's observatories are ready. Again, speculation, not fact. But the pattern persists. Trajectory, timing, chemistry, mass. Every anomaly points in the same direction, not toward a natural object, but toward something designed. And yet, the evidence remains circumstantial, suggestive, maddeningly incomplete. Because proving something is artificial requires more than anomalies. It requires positive evidence, a signal, a structure, a maneuver, something that natural processes cannot produce, no matter how rare or improbable. Atlas hasn't given us that yet. But it hasn't reached Mars yet either. On October 29th, when Atlas passes within 18 million miles of the red planet, 3 orbiters will be watching. MRO, the Mars Reconnaissance Orbiter, carries the HiRISE camera, capable of resolving features as small as a meter across from Martian orbit. At 18 million miles, the resolution won't be that sharp, but it will be enough to see if Atlas has structure. Geometry, panels or antennas or anything that reflects light in non-random patterns. TGO, the trace gas. Orbiter will perform spectroscopy, searching for emission signatures beyond nickel. If Atlas is outgassing hydrogen, oxygen or nitrogen, TGO will detect it. If it's emitting radiation in the infrared or microwave spectrum, TGO will measure it. Mars Express, the oldest active orbiter at Mars, carries the MARSIS radar instrument. Originally designed to probe beneath the Martian surface for water ice, MARSIS can also detect reflections from objects in space. If Atlas has a metallic surface, MARSIS might pick up echoes. 3 orbiters, multiple instruments, 1 chance. Because after October 29th, Atlas will continue inward toward the Sun, and our window for detailed observation will shrink. By the time it reaches perihelion in November, it will be too close to the Sun's glare for most telescopes. We'll get brightness curves, maybe some spectroscopy, but not the high-resolution data we need to settle the question. This is it. The trajectory brought Atlas here. The timing gave us a narrow opportunity. The chemistry and mass forced us to ask uncomfortable questions. Now we wait for the answer. 3 weeks. And the universe, indifferent as always, continues turning. Outgassing is one of the most predictable processes in cometary science. When a comet approaches the Sun, solar radiation heats its surface. Ice sublimates, turns directly from solid to gas, and escapes into space. Dust particles embedded in the ice are dragged along, creating the tail that makes comets visible from Earth. This process is governed by thermodynamics, fluid dynamics, and Newton's laws of motion. We've studied it for centuries. We've modeled it with precision. We know exactly what should happen. Atlas defies every model. The comet, if that's what it is, loses 150 kilograms of material every second. That's a bathtub full of mass ejected every few seconds. The vapor leaves the surface at 440 meters per second, faster than the speed of sound on Earth. That's a lot of force. Force produces acceleration. Newton's third law: for every action there is an equal and opposite reaction. If Atlas is expelling mass in one direction, the nucleus should recoil in the opposite direction. It doesn't. Astronomers measure non-gravitational acceleration by comparing an object's observed trajectory to the path predicted by gravity alone. The difference, if any, reveals forces beyond gravity. Outgassing comets show clear deviations, small but measurable. Atlas shows none. Its trajectory matches the gravitational prediction perfectly, as if the escaping vapor carries no momentum, as if momentum doesn't apply. Imagine standing on a frozen lake holding a fire extinguisher. You pull the trigger. The extinguisher sprays foam backward, and you slide forward across the ice. You can't prevent it. The conservation of momentum is absolute. Now imagine the extinguisher sprays, and you don't move. The foam shoots out, but you remain stationary. No sliding, no recoil. That's Atlas. The most immediate explanation would be symmetric outgassing. If vapor escapes equally in all directions, the forces cancel out. No net acceleration. But comets don't outgas symmetrically. Their nuclei rotate, creating active jets that point in specific directions. As the nucleus spins, the jets sweep across space like lighthouse beams. The force isn't balanced, it's directional. We see this in every active comet we've observed. Halley's Comet, Hale-Bopp, 67P, Churyumov-Gerasimenko, which ESA's Rosetta probe studied, up close. All of them showed non-gravitational acceleration consistent with asymmetric outgassing. Atlas is different. Perhaps its rotation rate is precisely tuned. Perhaps the jets activate and deactivate in patterns that balance perfectly. Perhaps its shape, still unknown, produces forces that cancel by geometric coincidence. Or perhaps Atlas compensates. If an object had thrusters, small, controlled propulsion systems, it could counteract the force of outgassing. It could maintain trajectory, despite mass loss. Why would anything need to do that? Navigation. If you're traveling between stars, even small deviations compound over thousands of years. A fraction of a degree off course, sustained across light years, and you miss your target entirely. You'd need correction, continuous subtle course adjustments. And if you're outgassing to blend in with natural comets, you'd need to compensate for the momentum that outgassing produces. This is speculation. It's a hypothesis built on the absence of acceleration, the absence of deviation. Absence isn't evidence, it's a void where evidence should be, but voids can be revealing. When Sherlock Holmes solved The Adventure of Silver Blaze, the key clue was a dog that didn't bark. The absence of an expected event pointed to the truth. Atlas's silence, its refusal to accelerate, despite outgassing, might be its loudest signal. Let's consider the alternatives. Maybe Atlas is massive enough that 150 kg/s of outgassing produces acceleration too small to measure. But we've already established a minimum mass of 33 billion tons. Even for that mass, the expected acceleration over weeks of observation should be detectable. Maybe the outgassing rate is wrong. Maybe it's slower than measurements suggest. But spectroscopy is reliable. The brightness and emission lines don't lie. Maybe there's a natural process we don't understand. Maybe comets from interstellar space formed in colder, darker environments behave differently than comets from our solar system. Maybe their structure, composition, or internal mechanics suppress non-gravitational acceleration. Maybe. But maybe is where speculation begins. And speculation, in science, is a tool, not a destination. We speculate to generate hypotheses. We test those hypotheses with data. And when the data arrives, when Atlas passes Mars, when the orbiters capture their observations, we'll know whether the speculation was justified. 3 weeks. 3 weeks until MRO, TGO, and Mars Express turn their instruments toward Atlas and search for answers. 3 weeks until we see whether the ghost has a shadow after all. Because something is casting light, something is emitting vapor, something is moving through our solar system with precision and silence. And we're about to find out what. Mars is the best vantage point we have. Not because it's special, because it's close. On October 29, 2025, Atlas will pass within 18 million miles of Mars. For context, Earth at its nearest is about 34 million miles from Mars. Atlas will come twice as close. That proximity matters. At 18 million miles, the resolution improves, the signal strengthens. The instruments in Mars orbit, designed to study the red planet's atmosphere, surface, and potential for life, become improvised observatories for an interstellar object. MRO, the Mars Reconnaissance Orbiter, has been circling Mars since 2006. It carries HiRISE, the high-resolution imaging science experiment, a camera so powerful it can photograph individual boulders on the Martian surface from orbit. From 18 million miles away, HiRISE's resolution drops dramatically, but it's still sufficient to resolve features larger than a few hundred meters on Atlas's surface. If Atlas has structure panels, protrusions, anything that breaks the smooth profile of a natural comet, HiRISE will see it. TGO, the Trace Gas Orbiter, arrived at Mars in 2016 as part of ESA's ExoMars program. Its primary mission is detecting trace gases in the Martian atmosphere, methane, water vapor, anything that might hint at biological or geological activity. But TGO also carries spectrometers capable of analyzing sunlight reflected off nearby objects. When Atlas passes, TGO will capture spectra across a wide range of wavelengths: visible light, infrared, ultraviolet. If Atlas is emitting anything beyond nickel, if there are organic compounds, water ice, or unusual materials, TGO will detect them. Mars Express is the oldest active Mars orbiter, launched by ESA in 2003. It carries MARSIS, a radar sounder designed to probe beneath the Martian surface for subsurface water. MARSIS sends radar pulses downward and listens for reflections. Those reflections reveal layers, ice deposits, and geological structures hidden below ground. But radar works in space too. If MARSIS points toward Atlas and transmits, it might receive echoes. The strength and timing of those echoes would reveal information about Atlas's surface, whether it's icy, rocky, or metallic, whether it's smooth or jagged, whether it reflects radar like a natural object or like something manufactured. This is our best chance. Not our only chance. Ground-based telescopes will continue observing Atlas through perihelion, but our best chance for high-resolution multi-instrument data. And the timing is tight. Atlas moves fast. At 137,000 miles per hour, it crosses vast distances in days. The orbiters will have only a narrow window, perhaps a few hours, when Atlas is close enough, for optimal observation. NASA and ESA have coordinated the campaign. Commands have been uploaded to the orbiters. Observation schedules have been locked in. Engineers have calculated pointing angles, exposure times, and spectral bands. Everything is ready, except us. Because the data that arrives on October 29th will force a decision. If Atlas shows structure, geometric features, reflective panels, anything inconsistent with a natural comet, then the artificial hypothesis gains weight, not proof, but momentum. If Atlas emits signals, radio waves, modulated light, anything that resembles communication, then the hypothesis becomes unavoidable. And if Atlas alters its trajectory as it approaches Mars, if it maneuvers in ways that gravity alone cannot explain, then we'll have to accept that something intelligent sent it. But what if the data shows nothing unusual? What if high-rise images reveal a lumpy, irregular nucleus, exactly what you'd expect from a comet? What if TGO's spectra detect water, ice, carbon monoxide, and iron after all? What if MARSIS receives no radar echoes, suggesting a surface too rough or icy to reflect coherently? Then Atlas becomes a mystery, not a revelation. An object that breaks some rules but not others, a natural phenomenon that challenges our models without rewriting them entirely. And the speculation fades, the excitement ebbs, the headlines disappear. We return to watching the skies, waiting for the next anomaly, hoping the universe will give us something clearer next time. That's the outcome most scientists expect, not because they lack imagination, not because they dismiss the possibility of artificial objects, but because anomalies usually resolve into natural explanations, because the universe is strange enough without invoking intelligence, because skepticism is the foundation of science, and skepticism says, extraordinary claims require extraordinary evidence. Atlas hasn't provided extraordinary evidence yet, but extraordinary evidence is coming. 3 weeks. 3 weeks until Mars. 3 weeks until the instruments activate, the data flows, and the mystery sharpens or dissolves. 3 weeks until we learn whether the ghost without shadow is natural or designed. And 3 weeks isn't long when you're waiting for an answer that could change everything. Because if Atlas is artificial, if it's a probe sent by an intelligence we've never met, then the question shifts. We stop asking, is anyone out there? We start asking, what do they want? And that question. When we search for extraterrestrial intelligence, we listen. Radio telescopes scan the sky for signals patterns in electromagnetic radiation that couldn't arise from natural processes. The search for extraterrestrial intelligence, SETI, has been listening since 1960. 65 years of silence, not complete silence. Space is noisy. Pulsars emit regular radio pulses. Magnetars flare. Quasars scream across billions of light years. But none of it is deliberate. None of it is a message. We've never detected a signal that says we are here. Until perhaps now. Atlas doesn't broadcast radio waves, it doesn't pulse in regular intervals, it doesn't beam messages toward Earth. But maybe that's not how you send a signal. Maybe you send an object instead. Think about communication across interstellar distances. Radio waves travel at the speed of light fast by human standards, but agonizingly slow across light years. A message sent from the nearest star system, Alpha Centauri, would take 4 years to arrive. A reply would take 4 more. 8 years for a single exchange. Now multiply that by thousands or tens of thousands of light years if the sender is farther away. Conversations become impossible. Even one-way messages require patience measured in generations, but a physical probe doesn't need to communicate in real time. It carries information with it. Data encoded in its structure, its materials, its behavior. It arrives, it's observed, and the message is delivered not through radio waves but through presence. Atlas's presence is its message. The nickel emission without iron, a chemical impossibility designed to attract attention. The ecliptic trajectory, a path chosen to pass near inhabited worlds. The lack of non-gravitational acceleration, a hint that something is compensating, controlling, maintaining course. These aren't transmissions, they're clues. And if Atlas is a probe, then October 29th isn't just an observation opportunity. It's a rendezvous. The question is, what happens during a rendezvous? In science fiction, first contact is dramatic. Ships descend, beings emerge, dialogue begins. But reality is rarely dramatic. It's incremental, cautious, and wrapped in uncertainty. If Atlas is artificial, first contact might look like this. A change in trajectory. A minor course correction as it approaches Mars, executed with precision that gravity can't explain. Not a landing, not a transmission, just a maneuver. And that would be enough. Because maneuvering proves intent. Natural objects don't steer, they fall, they drift, they obey gravity and momentum without deviation. Artificial objects choose. MRO, TGO, and Mars Express will be watching for that choice. Their instruments will track Atlas's position with precision, comparing observed motion to predicted motion. Any discrepancy, any deviation, no matter how small, will be recorded. And if Atlas maneuvers, the data will confirm it within hours. But there's another possibility. What if Atlas doesn't maneuver? What if it passes Mars without changing course, without signaling, without doing anything that distinguishes it from a natural comet? That doesn't disprove the artificial hypothesis. It just means the probe isn't designed to respond to our observation. Maybe it's passive, a recorder, not a communicator, something sent to collect data about our solar system planetary positions, compositions, electromagnetic signatures, and carry that data home. Or maybe it's dormant, waiting for a specific condition to activate, a certain distance, a certain alignment, a certain type of signal we haven't yet sent. Or maybe it already transmitted. Maybe Atlas sent its message weeks ago or months ago or years ago, long before we discovered it. A narrow beam radio pulse aimed at Earth or Mars or nowhere in particular. A signal we missed because we weren't listening at the right frequency, at the right time, in the right direction. SETI searches are limited. We can't monitor every frequency simultaneously. We can't watch the entire sky at once. If a signal arrived while our telescopes were pointed elsewhere, we'd never know. This is the problem with silence. It's ambiguous. Silence might mean no one is out there, or it might mean we're listening wrong, or it might mean they're here observing, waiting, and we haven't noticed yet. Atlas forces us to reconsider what a signal might look like, not a radio wave, an object, not a message in binary code. A puzzle written in chemistry and motion. And if we're right, if Atlas is a probe, then someone somewhere is waiting for us to solve it. The thought is unsettling, not because contact with extraterrestrial intelligence would be dangerous. That's a separate question, one we can't answer without knowing who sent the probe and why. What's unsettling is the implication. If Atlas is artificial, then intelligence exists beyond Earth. That's transformative. But it also means we've been watched, studied, possibly for decades, centuries, or longer, because Atlas didn't arrive yesterday. It's been traveling for thousands of years, maybe longer. If it was aimed at our solar system, then whoever launched it knew we were here, or knew we would be here by the time it arrived. They predicted us. Or they've sent many probes scattered across the galaxy, and Atlas is just one of thousands, a lottery ticket cast into the void, hoping to find something interesting. Either way, we're no longer alone in asking the question, is anyone out there? We're the answer to someone else's question, and that changes everything. 3 weeks until Mars, 3 weeks until the data arrives and the speculation ends or deepens. Because whether Atlas maneuvers or stays silent, whether it broadcasts or remains inert, the question won't fully resolve. We'll have more data, better observations, clearer images. But certainty? That's harder to come by. Even if Atlas shows structure, even if it maneuvers, even if it emits a signal, skeptics will demand more proof. They'll propose exotic natural explanations. They'll cite the lack of definitive communication as evidence against intelligence. And they'll be partly right. Because proving something is artificial requires more than anomalies. It requires intent, purpose, a message we can decode. Atlas might give us that. Or it might remain ambiguous, a ghost that refuses to speak, a shadow that won't solidify, a mystery that lingers just beyond certainty. And maybe that's the point. Maybe the message isn't in what Atlas does. Maybe it's in what Atlas makes us do. It makes us look. It makes us question. It makes us coordinate global observation campaigns, point our best instruments at an object we barely understand, and confront the possibility that we're not the universe's only engineers. That alone is worth something. Whether Atlas is a comet or a probe, whether it's natural or designed, it's already accomplished something extraordinary. It's made us wonder. And wonder, in the end, is what drives discovery. How do you recognize intelligence when it doesn't look like you? This isn't a philosophical question. It's practical, urgent. Especially now, with Atlas approaching Mars and time running short. We've spent decades imagining what extraterrestrial intelligence might look like. Movies, novels, and scientific papers have proposed everything from humanoid beings to energy clouds, from hive minds to artificial superintelligences. But imagination isn't preparation. When confronted with something real, something ambiguous, something that doesn't announce itself clearly, we hesitate, we debate, we demand more proof. Atlas is testing that hesitation. Consider the evidence so far. Impossible chemistry, massive outgassing without acceleration, a trajectory aligned with the ecliptic, and a close approach to Mars timed almost perfectly for observation. Each anomaly, taken alone, might have a natural explanation. Taken together, they form a pattern. And patterns suggest design. But suggesting isn't proving. The problem is this: intelligence doesn't always look like intelligence from the outside. A termite mound looks like a pile of dirt until you study its ventilation system. A beaver dam looks like fallen branches until you notice the engineering. Even human artifacts, stone tools, for instance, were once dismissed as natural rocks shaped by erosion. We recognize intelligence when we see purpose, when we see function, when we see something that accomplishes a goal in a way that randomness can't explain. Atlas might have a purpose, but we don't know what it is yet. If it's a probe, its purpose could be observation, studying our solar system from within, recording planetary positions, magnetic fields, atmospheric compositions, transmitting that data home or storing it for retrieval. If that's the case, Atlas wouldn't need to communicate with us. It wouldn't need to land, signal, or maneuver visibly. It would just need to watch. And we'd never know, unless it makes a mistake, unless it reveals itself accidentally, unless something in its design, a reflection, a thermal signature, a geometric feature, gives it away. That's what MRO, TGO, and Mars Express are searching for. The giveaway. The detail that can't be explained naturally. But here's the deeper problem. Even if we see something artificial, we might not recognize it as intelligence. Arthur C. Clarke once wrote that any sufficiently advanced technology is indistinguishable from magic. The corollary is equally important. Any sufficiently advanced technology might be indistinguishable from nature. If Atlas was designed by an intelligence millions of years ahead of us, Its construction might use principles we haven't discovered, materials we can't identify, processes that mimic natural phenomena so closely we assume they are natural. The nickel emission could be a byproduct of propulsion we don't understand. The lack of acceleration could result from physics we haven't theorized. The trajectory could be controlled by forces we can't measure. And we'd look at the data, scratch our heads and say, interesting comet, weird but natural. This is the recognition problem. It's not that we lack instruments or data. It's that we lack a framework for interpreting data that doesn't fit known categories. We've encountered this problem before. In 1967, astronomers Jocelyn Bell and Anthony Hewish detected radio pulses from space regular, precise, repeating every 1.3 seconds. The signals were so artificial-looking they nicknamed the source LGM-1, Little Green Men 1. But it wasn't intelligence, it was a pulsar, a rotating neutron star emitting beams of radiation like a cosmic lighthouse. Nature had mimicked a signal. The opposite could happen with Atlas. Intelligence could mimic nature so well that we dismiss it. So how do we avoid that mistake? We look for intent. Intent is what separates design from accident. A river carves a canyon. Through erosion, no intent. An engineer carves a canal for irrigation intent. If Atlas maneuvers, that's intent. If it emits a structured signal, that's intent. If its surface shows geometric patterns too regular to form naturally, that's intent. But intent can be subtle, hidden, disguised. Maybe Atlas's intent is to remain ambiguous, to test whether we're ready for contact by seeing if we can solve the puzzle, to provoke curiosity without offering certainty. If that's the case, then demanding. Proof is exactly the wrong response, because proof might never come. Not in the way we expect, not in the form of a radio message or a landing or a handshake. The proof might be the pattern itself, the accumulation of anomalies, the weight of improbability pressing down until we're forced to accept the simplest explanation, even if that explanation is extraordinary. Occam's razor says the simplest explanation is usually correct, but simplicity is relative. Is it simpler to propose a new type of comet that violates chemistry, defies momentum, and arrives on a statistically improbable trajectory? Or is it simpler to propose that someone sent it? The answer depends on your assumptions about the universe. If you assume intelligence is rare, perhaps unique to Earth, then the comet explanation is simpler. Add enough unknowns, propose enough exotic processes, and you can fit the data into a natural framework. But if you assume intelligence is common, if you accept that billions of stars host billions of planets and some fraction of those planets might develop civilizations, then the artificial explanation becomes simpler. Why invent new chemistry when existing technology suffices? We don't know which assumption is correct. We won't know until we have more data. And the data is coming. 3 weeks until the orbiters observe Atlas up close. 3 weeks until we see whether recognition is possible or whether ambiguity is all we'll ever have. Because even if Atlas is a probe, even if it's unambiguously artificial, that won't answer the deeper questions. Who sent it? When? Why? And most importantly, are they still out there, waiting to see if we notice? The recognition problem doesn't end with identifying intelligence. It begins there. Because once you recognize intelligence, you have to decide what to do about it. Do you respond? Do you stay silent? Do you celebrate the discovery or fear it? Those questions are coming too, faster than we're ready for. And the universe, indifferent as always, watches to see what we choose. Certainty is comforting, ambiguity is not. We crave answers, clean conclusions, data that points clearly in one direction and allows us to move forward with confidence. Atlas offers none of that. Instead, it offers a puzzle with missing pieces, a story with multiple endings, and a question that grows sharper the more we examine it. The scientific community is divided, not into camps of believers and skeptics that's too simplistic, into gradients of probability. Some researchers estimate a 5% chance Atlas is artificial. Others say 30%. A few cautious voices whisper 60% but won't commit to print. No one says 100%. No one says 0. Because the data supports both interpretations, natural and artificial. Coincidence and design, chaos and purpose, and that ambiguity is exhausting. Scientists are trained to weigh evidence, calculate probabilities, and suspend judgment until data resolves uncertainty. But when data doesn't resolve uncertainty, when every new observation sharpens the question instead of answering it, frustration sets in. Some researchers have stopped following Atlas entirely, not because they've lost interest, but because the ambiguity is maddening. Every headline promises revelation, every paper offers another anomaly, and still no consensus. Others double down. They refine models, propose new observations, argue in journals and conferences about what the data really means. They pass spectra line by line, searching for the detail that will tip the balance. And a small group does something different. They prepare. They prepare for the possibility that Atlas is artificial, that on October 29th, when the orbiters observe it up close, the data will show something undeniable, a structure, a signal, a maneuver. And if that happens, the world will change overnight, not because of the object itself, because of what it represents. Proof of extraterrestrial intelligence would be the most significant discovery in human history. It would answer a question we've asked since we first looked up at the stars. Are we alone? The answer would be no. And that answer would ripple through every aspect of human civilization. Science would pivot. Billions in funding would flow towards studying Atlas, decoding its purpose, understanding its origins. Telescopes would scan the skies for more objects like it. New missions would launch to intercept, study, or communicate. Philosophy would grapple with our place in the universe. Are we primitive, advanced, somewhere in the middle? If someone built Atlas, what does that say about intelligence, consciousness, and the trajectory of civilizations? Religion would confront questions of creation and purpose. Some traditions might integrate the discovery seamlessly, others might fracture, and millions of people would search for meaning in a cosmos suddenly more crowded than they imagined. Politics would fracture too. Who speaks for Earth? Who decides whether we respond to Atlas and how? The United Nations has a protocol for responding to extraterrestrial signals, but protocols are fragile when confronted with reality. And then there's fear, not panic, not apocalyptic terror, but a quiet, persistent unease. If Atlas is a probe, then someone sent it. And if someone sent it, they know we're here. They've studied us, perhaps for decades or centuries. They might be watching now. What do they want? That question matters because history offers uncomfortable lessons. When technologically advanced civilizations encounter less advanced ones, the results are rarely equal. Colonization, exploitation, displacement. We're used to being the advanced civilization, the ones doing the exploring, the ones making first contact. Atlas inverts that dynamic. If it's artificial, we're the ones being explored, and we have no idea what intentions guide the explorers. Maybe they're benevolent, maybe they're indifferent, maybe they're merely curious, and their curiosity has no moral weight, just as our curiosity about ants doesn't prevent us from building roads through their colonies. This is why ambiguity matters. As long as Atlas remains ambiguous, we can avoid these questions. We can continue debating natural versus artificial, weighing probabilities, publishing papers, and maintaining the comfortable distance of uncertainty. But if the ambiguity collapses, if the data on October 29th is undeniable, then the questions stop being theoretical. They become urgent, and urgency demands action. What action? That depends on what Atlas does. If it maneuvers, we track it. If it signals, we listen. If it reveals structure, we study it. If it does nothing, we wait and wonder whether inaction is itself a message. The problem is timing. 3 weeks isn't long enough to prepare globally. Not really. Governments move slowly. International cooperation requires negotiation, consensus, and trust is fragile. When the stakes are this high, if Atlas proves artificial, some nations will want to respond immediately. Others will urge caution. A few might see it as a threat and propose defensive measures. And all of this will unfold in public. Because Atlas isn't a classified project. It's visible to anyone with a telescope. The data will be published. The debate will be open. That's both reassuring and terrifying. Reassuring because transparency prevents secrecy, paranoia, and unilateral decisions. Terrifying because transparency also means chaos, millions of voices, opinions, and fears colliding in real time. We're not ready for that, but we might not have a choice. Because Atlas doesn't care whether we're ready. It's already here, already approaching Mars, already forcing us to confront possibilities we've avoided for generations. And the ambiguity that protected us from those possibilities is shrinking. 3 weeks until Mars. 3 weeks until the data forces a reckoning. And the universe, vast and indifferent, continues its turn. October 29, 2025. Atlas passes Mars. The orbiters activate. Cameras point. Spectrometers engage. Radar pulses transmit and wait for echoes. For 3 hours, MRO, TGO, and Mars Express observe the object at their closest approach, 18 million miles. Not close by human standards, that's 70 times the distance from Earth to the Moon, but close enough for precision. High rise captures images, hundreds of them. Long exposures to gather faint light, each frame processed, stacked, and analyzed for features. TGO records spectra across 20 wavelengths, visible light, infrared, ultraviolet, searching for emission lines, absorption bands, thermal signatures. Marsis sends radar pulses toward Atlas and listens, measuring echoes, timing delays, analyzing reflections. The data streams back to Earth at the speed of light. 12 minutes. That's how long it takes for radio signals to cross the gap between Mars and Earth when the planets are aligned as they are now. By early afternoon UTC, the first images arrive. Scientists at NASA's Jet Propulsion Laboratory in California and ESA's Operations Center in Germany download the files. Preliminary processing begins immediately. Noise reduction, calibration, enhancement, and then silence. Not literal silence. Servers hum, keyboards click, colleagues murmur as they lean toward monitors, but communicative silence, the kind that means something unexpected has appeared. Within an hour, the first image leaks, not officially, a low-resolution preview shared on a private message board by someone with access to the raw data. The image spreads quickly, Twitter, Reddit, science forums, news sites scrambling to verify authenticity. It shows Atlas, blurry, distant, a smudge of light against the black, but not a round smudge, not the irregular potato shape of a typical comet nucleus, elongated, smooth, almost cylindrical. Within 3 hours, NASA releases an official statement. Brief. Cautious. Initial observations of Object C 2024 Atlas have been successfully completed by Mars orbiters. Preliminary data shows features requiring further analysis. A press conference will be held October 31st to present findings. 2 days. They're asking for 2 days before going public with details. The internet doesn't wait. Analysts, amateur astronomers, and image processing enthusiasts download the preview image and enhance it. Contrast adjustments, edge detection, sharpening algorithms. The shape clarifies. Long axis approximately 6 times longer than the short axis. Smooth edges, no visible jets or outgassing plumes. It doesn't look like a comet. TGO's spectroscopy data leaks next. Not images this time, numbers, wavelengths and intensities. Raw measurements that require expertise to interpret, but experts are watching. Within hours, preliminary analyses appear on preprint servers. Nickel emission confirmed, stronger than ground-based observations suggested. Iron emission. Still absent, but something new. A faint line at 589 nanometers, sodium, and another at 818 nanometers, unknown origin, possibly argon, possibly something else. And in the infrared, a thermal signature inconsistent with ice. The object is warmer than it should be for a comet at that distance from the Sun. Not dramatically warmer, just off. The Marsis radar data doesn't leak. It's released officially on October 30th, with minimal commentary. The radar detected reflections. Strong ones. The surface of Atlas reflects radio waves like metal, not like ice, not like rock, metal. The press conference on October 31st is watched by 200 million people. live-streamed globally, translated into 40 languages. NASA's lead scientist, a soft-spoken woman with decades of experience studying comets, delivers the findings carefully. She presents images, spectra, radar data. She emphasizes uncertainty, preliminary results, need for further observation. And then she says it. At this time, we cannot conclusively determine whether Object C-2024 Atlas is a natural body or an artifact of non-terrestrial origin. Cannot conclusively determine. The phrasing is precise. Diplomatic. It acknowledges both possibilities without committing to either. But the damage or revelation, depending on perspective, is done. The headline writes itself, NASA. Atlas might be artificial. Markets react. Stock indices drop 2% in an hour, then recover. Gold spikes. Cryptocurrency communities erupt in speculation. Religious leaders issue statements. Some embrace the possibility. Others urge caution. A few outright reject it. Social media fractures into tribes, believers, skeptics. Conspiracy theorists convinced this is a distraction from terrestrial problems. Futurists celebrating humanity's potential first contact. And through it all, Atlas continues moving. It's past Mars now, heading inward toward the sun, toward perihelion, toward the moment when it will be brightest, most active, most observable. November 17th, 18 days away. The October 29th data didn't resolve the mystery, it deepened it. Atlas has structure, it reflects radar like metal, it emits elements that shouldn't appear together, and its thermal signature defies the models. But none of that proves intent, none of that confirms intelligence. A metal-rich asteroid ejected from another star system might show similar properties. Exotic chemistry forged in an alien stellar furnace could explain the nickel without iron puzzle. Thermal gradients on a rotating body might account for the infrared anomaly. The shape smooth, elongated is harder to explain naturally, but not impossible. Oumuamua was elongated too. Some models proposed it was a fragment of a larger body, sheared apart by tidal forces during a close stellar encounter. The same might apply to Atlas. Might. The ambiguity persists, sharpened but not collapsed. And now the world is watching, not just scientists, everyone. Because the data from October 29th accomplished something unintended. It made Atlas undeniable. Before it was a curiosity, an anomaly discussed in academic papers and niche astronomy forums. Now it's front-page news, dinner-table conversation, a topic that spans disciplines, cultures, and ideologies, and in 18 days it reaches perihelion. Whatever Atlas's comet, probe, fragment, artifact, it will be at its most active point, closest to the sun, hottest, brightest. If it's going to do something, that's when it will happen. Telescopes around the world are already reserving time. Observation schedules have been rearranged. Instruments that were pointed at galaxies, black holes, and exoplanets are now pointed at a single object in our own solar system, waiting. Because the data that arrived on October 29th answered some questions and raised 100 more. And the universe, indifferent as always, offers no hints about what comes next. Would we even recognize intelligence if it wasn't biological? This isn't abstract philosophy anymore, it's operational. Urgent, because Atlas might be forcing us to answer it. Intelligence, as we understand it, arises from biology. Neurons, brains, evolutionary processes that favor survival, replication, adaptation. Consciousness, whatever that means, emerges from complexity. But intelligence doesn't require biology. We've known that theoretically for decades. Artificial intelligence, even in its current primitive form, demonstrates that information processing doesn't need cells, synapses, or organic chemistry. It needs structure, logic, patterns. And patterns can exist in many substrates. Silicon, quantum states. Perhaps even in arrangements of matter we haven't imagined. If Atlas is artificial, it might not be a spaceship in the traditional sense. No crew, no windows, no pilots steering it through the void. It might be autonomous. A machine intelligence sent on a journey spanning millennia, programmed, designed, launched, and then left to operate independently. Or it might be something stranger. What if Atlas isn't a probe at all? What if it's a life form? Not biological life, not cells and DNA, but something that fits the functional definition: self-organization, response to stimuli, metabolism, reproduction. Imagine an intelligence that exists as a structured process rather than a discrete organism. Information encoded in magnetic fields, consciousness distributed across plasma or electromagnetic interactions. Mind without a brain. We wouldn't recognize that as intelligence. We'd call it a phenomenon, a natural process, an anomaly, and we'd miss it entirely. This is the problem Atlas exposes. Our definitions are too narrow. Our expectations are too Earth-centric. We look for radio signals because we use radio. We search for planets with liquid water because we need water. We assume intelligence builds cities, writes languages, and sends messages because that's what we do. But intelligence that evolved, under different conditions on different timescales, with different physical constraints, might not resemble us at all. It might not communicate in ways we expect. It might not value the things we value. It might not even perceive time the way we do. If Atlas was designed by such intelligence, how would we know? The answer: we might not. Not definitively. Not without communication. And communication requires common ground, shared concepts, a language mathematical, visual, logical, that both sides can decode. Atlas hasn't communicated yet, not in ways we understand, but maybe it has and we missed it. The nickel emission could be a marker, a deliberate choice of chemical signature designed to stand out against the background of natural comets. The ecliptic trajectory could be a greeting, an alignment that says, "I see your planets, I'm approaching on your terms." The smooth, elongated shape could be intentional. A form chosen not for aerodynamic space has no air, but for recognizability, something that doesn't look random. These are signals, subtle, indirect, but signals nonetheless. And if we're right, then Atlas is waiting for us to signal back. But how do you signal something you're not sure is listening? This question has occupied researchers for decades. SETI protocols assume a two-way exchange. We detect a signal, we respond with a signal of our own, and dialogue begins. But Atlas isn't transmitting radio waves. It's not flashing lights. It's not doing anything we'd conventionally call communication. So what do? Some researchers have proposed sending a directed radio message toward Atlas, a simple pulse, a mathematical sequence, something that says, "We see you. We're intelligent too." Others argue against it. If Atlas is artificial, and if its creators are hostile or indifferent, drawing attention to ourselves might be dangerous. This is the oldest debate in SETI: to transmit or not to transmit, to announce our presence or remain silent. And Atlas forces the debate into real time, because we have 18 days. 18 days until perihelion. If we're going to send a message, it needs to happen soon. But even if we send one, will Atlas respond? Maybe. Maybe not. Maybe it's not designed to respond to us at all. Maybe its mission is observation, not communication. Maybe it records data, waits for retrieval, and never acknowledges the beings it studies. That possibility is unsettling. The idea that we might be observed without consent, studied without interaction, is deeply uncomfortable. It inverts every assumption we have about exploration and contact. We're used to being the explorers, the ones making first contact, the ones deciding how and when interaction happens. Atlas takes that agency away. If it's a probe, we're not the discoverers, we're the discovered. And that changes the psychology of the moment. Suddenly we're not asking, what will they be like? We're asking, what do they think of us? Are we interesting? Primitive, dangerous, irrelevant? Do they see potential in humanity, or do they see a species barely capable of leaving its own planet? These questions are impossible to answer without communication, but they weigh on the conversation nonetheless. Because first contact, if that's what this is, isn't just about exchanging information, it's about identity. about how we see ourselves reflected in the gaze of another intelligence, and we're not sure we're ready for that reflection. 18 days. 18 days until perihelion. 18 days until Atlas reaches its brightest point, and either reveals something new or remains maddeningly ambiguous. The universe, indifferent as always, offers no reassurance, but the question persists. Would we even recognize intelligence if it wasn't like ours? And if we failed to recognize it, would that say more about the universe or about us? November arrives cold and clear across much of the northern hemisphere. The skies darken early, and in those darkening skies, astronomers prepare for the most observed event in modern history, perihelion, November 17th. The moment when Atlas passes closest to the Sun. At 0.65 astronomical units, about 60 million miles, Atlas will be well inside the orbit of Venus, closer to the Sun than Mercury ever gets, and at that distance, solar radiation will be intense. If Atlas is a comet, the heat will vaporize ice at an accelerated rate. Outgassing will peak. The tail, if there is one, will stretch across millions of miles. Brightness will increase dramatically, possibly making Atlas visible to the naked eye from Earth. If Atlas is artificial, perihelion might trigger something else. Activation, transmission, a change in behavior designed to occur at a specific solar distance. Both scenarios are possible. Both are being prepared for. Observatories around the world have coordinated their efforts. The James Webb Space Telescope, usually focused on distant galaxies and exoplanet atmospheres, has carved out time to observe Atlas in infrared. The Hubble Space Telescope will capture visible light images at maximum resolution. Ground-based telescopes in Chile, Hawaii, and South Africa are ready. And in orbit around Mars, the 3 spacecraft that observed Atlas in October remain on standby. They can't see it anymore. Atlas has moved too far inward, but their data from October 29th continues to be analyzed, frame by frame, spectrum by spectrum, searching for details that might have been missed. 1. Detail emerged last week, subtle, almost lost in the noise. In the high-rise images processed with advanced enhancement algorithms, a faint pattern appeared on Atlas's surface. Not random, not natural texture, regularity, lines, parallel, evenly spaced. Too faint to measure precisely, but distinct enough to suggest structure. The discovery wasn't announced publicly. It appeared in a preprint paper uploaded to Archive, an open repository for scientific research. The paper's title, Potential Surface, features on Interstellar Object C 2024. Atlas Preliminary Analysis, Potential Preliminary. The language is cautious, but the images are not. Enhanced, sharpened, filtered, they show something that doesn't look like erosion, impact craters, or tectonic fractures. They show geometry. Within hours, the paper was downloaded 50,000 times. Independent analysts confirmed the processing methods. Skeptics searched for artifacts, digital noise, compression errors, anything that might explain the patterns as illusion. Some found alternative explanations: shadows cast by irregular topography, reflections from ice layers, pareidolia, the human tendency to see patterns where none exist. Others found the explanations unconvincing because the lines aren't isolated. They appear in multiple frames from different angles under different lighting conditions, and they're parallel, consistently parallel. Nature rarely produces parallel lines. Rivers meander, cracks branch. Impact craters are circular, not linear. Parallel lines suggest intentionality, planning, design. The paper's authors don't claim Atlas is artificial. They present the data, describe the processing methods, and conclude with a careful statement. Further observations at perihelion may clarify whether these features are naturally occurring or indicative of non-natural processes. Non-natural processes, a diplomatic way of saying we don't know what we're looking at, and in 9 days we might find out. Because perihelion isn't just the moment of closest approach, it's the moment of maximum activity, maximum brightness, maximum opportunity. If Atlas has something to reveal, that's when it will happen. Ground control centers in 3 continents are running simulations. Engineers are double-checking pointing coordinates. Data storage systems are being cleared to handle the incoming flood of information. Everyone is ready, except maybe us. Because if Atlas shows something undeniable at perihelion, structure, signals, maneuvers, the world changes overnight. We stop being alone. We stop wondering if intelligence exists elsewhere. We start wondering what comes next. And 9 days isn't much time to prepare for that. The countdown continues. Telescopes align, observation schedules lock in, and Atlas, silent and swift, continues its dive toward the sun. November 17th, 2025, 1422. UTC. Atlas reaches perihelion, 60 million miles from the sun, closer than Venus, deep in the furnace of solar radiation. Telescopes around the world are locked on target. Hubble JWST, the Very Large Telescope in Chile, Keck in Hawaii, dozens of smaller observatories coordinating their efforts. For 3 hours they watch, and Atlas responds. Not with silence, not with the passive reflection of sunlight we'd expect from a comet, with light. At 15:07 UTC, 45 minutes after perihelion, Atlas brightens. Not gradually, suddenly. The change is dramatic. Brightness increases by a factor of 30 in less than 10 seconds. The object, previously a faint point visible only through professional telescopes, becomes visible to anyone with binoculars. Spectroscopy reveals the source. The nickel emission lines, already anomalous, intensify. New lines appear: copper, zinc, elements that weren't visible before, and in the blue part of the spectrum, something extraordinary, a glow, steady, artificial-looking. Atlas is shining blue, not reflecting blue light, emitting it. For 2 minutes, the glow persists. Then at 15:09 UTC it pulses, once, twice, 3 times. Each pulse lasts exactly 1.3 seconds. The interval between pulses, 2.7 seconds. The pattern is unmistakable, regular, precise, timed. And then it stops. The blue glow fades. The brightness drops back to baseline. Atlas returns to its previous state, a faint, distant object receding from the sun. But the damage is done. Or the revelation, depending on your perspective. Because natural objects don't pulse in regular intervals. They don't emit synchronized flashes of light with mathematical precision. Atlas just signaled. Within an hour, the data is confirmed across multiple observatories. The pulses were real, recorded independently by instruments on 4 continents. Within 2 hours, NASA and ESA release a joint statement. At approximately 15:07 UTC, Object C 2024. Atlas exhibited non-random light emission patterns. Analysis is ongoing. Further updates will follow as data is reviewed. Non-random, the most carefully chosen words in scientific history. Because random means natural, non-random means something else, and the world understands immediately. Social media explodes. News networks interrupt regular programming. Governments convene emergency meetings. The question everyone is asking, was that first contact? Scientists are more cautious. They use words like anomalous behavior and requires further study. They emphasize that one event doesn't constitute proof of intelligence. But privately, many are convinced, because the pattern fits no known natural process. Thermal expansion doesn't pulse with precision. Outgassing doesn't flash in regular intervals. Ice sublimation doesn't glow blue. The pulses were deliberate, controlled, timed to occur at perihelion, the moment when every telescope on Earth was watching. If you wanted to be noticed, that's exactly what you'd do. And Atlas was noticed. Within 12 hours, over 2 billion people have seen the footage. The light curve, a graph showing Atlas's brightness over time, becomes the most recognized scientific image in history. 3 pulses, evenly spaced, unmistakable, and then silence. Because after the pulses, Atlas doesn't repeat the signal. It doesn't change trajectory. It doesn't transmit radio waves or alter its spectrum. It just continues outward, away from the sun, away from Earth, back into the cold darkness of space, as if the message was complete, as if 3 pulses were all we needed. 3 pulses, 1.3 seconds each, 2.7 seconds apart. Is that a message? And if so, what does it mean? Within hours of the perihelion event, researchers around the world begin analyzing the pattern. Mathematicians, linguists, computer scientists, anyone with expertise in pattern recognition and communication theory. The numbers themselves are suggestive. 1.3 and 2.7, not round numbers, not obvious multiples, but someone notices something. The ratio, 2.7 divided by 1.3 equals approximately 2.08, close to 2, very close. Could the pattern be binary, on-off, a simple representation of the number 2? It's possible, but speculative. Others look for deeper meaning. Could 1.3 represent something physical, a wavelength, a frequency, a universal constant? In physics, there's a number close to 1.3, the mass ratio of a proton to an electron multiplied by a certain factor, obscure but intriguing. And 2.7, in cosmology that number is significant. The cosmic microwave background radiation, the afterglow of the Big Bang, has a temperature of 2.7 Kelvin. Could Atlas be referencing fundamental properties of the universe? Maybe, maybe not. The human mind is excellent at finding patterns, even when none exist, but the simplest interpretation remains the most compelling. Atlas pulsed 3 times to show intent, not to transmit complex data, not to encode star maps or mathematical proofs, just to say, I'm here, I'm not random, I'm deliberate, and that might be all the message we need, because the content of the message matters less than the fact that there was a message at all. Atlas chose perihelion, chose the moment of maximum visibility, chose a pattern regular enough to be unmistakable, but simple enough to avoid ambiguity. It wanted to be recognized as intelligent, and it succeeded. But recognition brings responsibility. Within days, the question shifts from what did Atlas say to how do we respond? Should we respond at all? Some scientists argue yes. If Atlas is a probe sent by another civilization, its creators deserve acknowledgement, a signal back, a confirmation that we received the message and understood its significance. Others argue no. We don't know who sent Atlas. We don't know their intentions. Responding might reveal our position, our capabilities, our vulnerabilities. Better to observe, to learn, to wait. The debate is fierce and unresolved because there's no protocol for this, no established procedure. The United Nations Office for Outer Space Affairs has guidelines for responding to extraterrestrial signals, but they're vague, aspirational, not actionable. And time is running out. Every day Atlas moves farther from the sun, farther from Earth. If we're going to send a message, it needs to happen soon. Radio signals travel at the speed of light fast, but not instantaneous. By the time a signal reaches Atlas, it will be tens of millions of miles away. And if there's a response, it will take just as long to return. We're talking about weeks, maybe months. And in the meantime, Atlas remains silent. No additional pulses, no trajectory changes, no signals in radio, infrared, or any other wavelength. It delivered its message and stopped, as if waiting to see what we do next. On November 22nd, 5 days after perihelion, a decision is made, not by governments, not by international bodies, but by scientists. A coalition of research institutions, NASA, ESA, the SETI Institute, and university observatories in 7 countries, agrees to send a response. The message is simple: a radio transmission aimed at Atlas's projected position, a sequence of prime numbers, mathematical proof of intelligence, followed by a representation of our solar system, 8 planets, 1 star, and a marker for Earth. The transmission lasts 10 minutes. Broadcast from the Arecibo-class radio telescope in China, the largest dish on Earth. Then silence, waiting. Because if Atlas is listening, if its creators are monitoring, we'll know within weeks. A response would take time, to travel back. But if it comes, if we receive any acknowledgement, it will be the most significant moment in human history. First contact, real, confirmed. undeniable. But weeks pass, and nothing comes. Atlas continues outward, past Mars, toward the outer solar system, and the radio silence persists. No response, no acknowledgement, no change in behavior, and slowly the world begins to accept a possibility. Atlas might not respond. Not because it can't, because it won't. Maybe the mission is observation, not communication. Maybe Atlas recorded our response, our message, our reactions, our global coordination, and that data is enough. Maybe we're not meant to have a conversation, just a moment of recognition, and maybe that's sufficient. December 2025. Atlas is now beyond Mars, heading toward the asteroid belt, still visible to large telescopes but fading. In a few months it will be too distant to observe with current instruments, and it will leave, exit the solar system, return to interstellar space, carrying with it the data it collected, the observations it made, the moment it pulsed, and the moment we responded. We'll never know what happens to that data, whether it's transmitted home, whether anyone receives it, whether our response mattered, but something has changed, not in space, in us. Because Atlas, whatever it is, has shaken something loose. A certainty we didn't realize we were holding on to. The certainty that we're alone. For all of human history, we've looked up at the stars and wondered, are we the only ones? Is intelligence rare? Are we the universe's only voice? Atlas answered that question, not with words, not with proof that satisfies every skeptic, but with presence, with chemistry that shouldn't exist, with a trajectory that defies chance, with pulses at perihelion that pattern themselves too precisely to be random. Atlas might be artificial, it might be natural. The debate will continue for years, but the doubt is gone. We're no longer certain we're alone, and that uncertainty, that crack in our cosmic solitude, changes everything. Funding for space exploration has doubled. New telescopes are being built. Missions to intercept future interstellar objects are being planned. SETI programs have expanded. More radio dishes scanning the sky. More computing power analyzing signals. More researchers dedicating their lives to the search for intelligence beyond Earth. Universities are teaching courses on interstellar communication. On the ethics of first contact. On how civilizations might encode messages in objects instead of signals, and children, millions of them, are looking up at the night sky and dreaming of other worlds, other beings, other intelligences, asking the same questions we've been asking. That's what Atlas has given us, not answers, but permission to dream, permission to believe that the universe is more than emptiness and silence, that somewhere, out there, others exist, others who built something, sent it across the stars and hoped it would be noticed. And it was. We noticed, we studied, we responded. Whether that response reaches anyone, whether it matters in the cosmic scale, we don't know. But we tried. And trying is what defines us. What is Atlas? After months of observation, thousands of scientific papers and countless hours of debate, we still don't have a definitive answer. We know what it did. We know how it behaved. We know the anomalies it presented. But we don't know what it is. And maybe that's the point. Because Atlas has taught us something more important than its identity. It's taught us humility. For centuries, we've assumed we understand the universe. We've built models, written equations, predicted behaviors, and mostly, we've been right. But Atlas doesn't fit the models, it breaks the equations, it defies predictions, and that's uncomfortable, unsettling, maddening. But it's also necessary, because the universe is larger than our understanding, stranger than our theories, more complex than our assumptions. Atlas reminded us of that. It reminded us that anomalies matter, that the things that don't fit are often the things that teach us the most. It reminded us that intelligence might not look like we expect, might not communicate the way we communicate, might not share our values, our priorities, our methods. And it reminded us that some questions take time to answer, that mystery is part of discovery, that living with uncertainty is part of being curious. We wanted Atlas to be simple, a comet or a probe, natural or artificial, a clear answer we could write down and move on from. But Atlas refused simplicity. It remained complex, ambiguous, unresolved, and in doing so it forced us to grow, to accept that not everything can be explained immediately, that some discoveries unfold slowly, that patience is as important as technology. We're still watching Atlas, still analyzing data, still hoping for clarity. But even if clarity never comes, even if Atlas fades into the distance without revealing its secrets, it's already given us something invaluable. A reminder that the universe is full of wonders, that exploration is worthwhile, that asking questions even when answers are elusive is what makes us human. On a cold evening in January 2026, a child in Brazil looks up at the stars. She doesn't know the names of the constellations, doesn't understand the distances involved, doesn't know that light from those stars has been traveling for years, sometimes centuries, to reach her eyes. But she knows about Atlas. She's heard the stories, seen the images, watched the videos of the pulses at perihelion, and she wonders, is someone out there? Did they send Atlas? Are they watching us now? Her parents don't have answers, no one does, but they tell her, keep looking, keep wondering, keep asking questions, because that's what we do. That's what makes us explorers. And someday, maybe not in her lifetime, maybe not for generations, someone will find an answer. Another object will arrive, another signal will be detected, another mystery will unfold, and humanity will be ready. Not because we have all the tools, not because we've solved every problem, but because we're curious, because we dream, because we refuse to accept that the universe is silent and empty. Atlas proved that refusal is justified. It proved that the universe holds surprises, that anomalies exist, that some things, whether natural or artificial, defy easy categorization. And it proved that looking up is never wasted effort, because even if we don't find what we're searching for, even if the answers remain elusive, the search itself transforms us. It makes us braver, wiser, more humble. It reminds us that we're part of something larger, a cosmos that's been here for billions of years and will be here for billions more. And in that vastness, in that incomprehensible scale, we're a small voice asking a simple question. Is anyone else out there? Atlas didn't answer that question, not completely, but it whispered back. And sometimes a whisper is enough. Atlas is leaving. By February 2026, it's crossed the orbit of Mars. By April, it will be in the asteroid belt. By summer, approaching Jupiter's orbit. And eventually, years from now, it will exit the solar system entirely, return to the space between stars, continue whatever journey it began millennia ago. We'll lose track of it. The signal will fade, the data will stop, and Atlas will become memory, a story we tell, an event we reference, a moment in history when something extraordinary happened and we were here to witness it. But its impact will remain. Not in technology. Atlas didn't give us new inventions or scientific breakthroughs. Not in politics, it didn't unite governments or resolve conflicts. But in perspective, Atlas changed how we see ourselves. Before Atlas, we were the center of our own story, the only intelligence we knew, the only voice in a silent cosmos. After Atlas, we're part of something larger. Maybe not alone, maybe observed, maybe one of many civilizations scattered across the galaxy, each wondering the same things. That shift is subtle, but profound, because it means we're not the end point of evolution, not the pinnacle of intelligence, not the universe's only experiment in consciousness. We're participants, one among many, or at least one among a possible many. And that realization is humbling, terrifying, and strangely comforting. Humbling, because it reminds us how small we are, how recent, how fragile. Terrifying because it means we're not in control, not the masters of the cosmos, not the arbiters of what's possible. And comforting because it means we're not alone in asking the hard questions. Others, if they exist, are asking too. What is the universe? Why does it exist? What is our place in it? Atlas suggests those questions are universal. That intelligence, wherever it arises, wonders. And wonder is the beginning of everything. Years from now, scientists will still debate Atlas. Was it natural? Was it artificial? Was it something in between a category we haven't named yet? The debate will never fully resolve, because certainty requires proof, and proof requires evidence we may never obtain. But the debate matters less than what it represents. It represents our refusal to stop asking, our insistence that mysteries deserve attention, our belief that the universe, strange and vast as it is, can be understood, at least partially. Atlas will appear in textbooks, in documentaries, in classrooms where children learn about the solar system and the objects that pass through it, and those children will ask, was it aliens? And their teachers will say, we don't know. Maybe, maybe not. But we're still looking. And that answer, honest, humble, hopeful, is the best one we have. Because science isn't about having all the answers, it's about asking the right questions and following them wherever they lead. Atlas led us to the edge of certainty, to the boundary between the known and the unknown. It showed us that boundary is thinner than we thought, that mysteries are closer than we assumed, that the universe, even in our own solar system, holds surprises. And it left us with a gift, the knowledge that surprise is still possible, that wonder still exists, that the night sky, vast and ancient and indifferent, still has stories to tell. And we're here to listen. On a quiet night in late 2026, an astronomer sits alone in an observatory dome. The telescope tracks a distant point of light too faint for the naked eye, but visible through the lens. Atlas, still moving, still silent, still mysterious. The astronomer doesn't expect answers, doesn't hope for signals, doesn't imagine the object will suddenly change course or transmit a message, but she watches anyway. Because watching is what we do. It's what we've always done. Long before telescopes, long before science, long before we understood what stars were, we looked up, and we wondered. Atlas reminded us that wondering is enough, that curiosity, even without certainty, is valuable, that the search for understanding is its own reward. We may never know what Atlas was, where it came from, what it meant, but we'll remember that it was here, that it challenged us, that it made us question, debate, and dream. And in the end, that's all any visitor, human or otherwise, can hope to do, to leave an impression, to spark a question, to remind us that the universe is larger, stranger, and more wondrous than we ever imagined. Atlas did that, and because of it, we'll keep looking up, we'll keep searching, we'll keep asking, what else is out there? And someday, maybe tomorrow, maybe in 1,000 years, the universe will answer. Until then, we have the night sky, the stars, the memories of an object that passed through our system and left us changed. Atlas, the impossible object, the visitor we'll never forget, and the reminder that in this vast ancient cosmos, mystery is not a problem to be solved, it's an invitation to explore.